All right. I think we're close enough here to the top of the hour, and we just hit 11. So, Rob, you're welcome to go ahead and kick us off.
Well, thank you very much, Brandon. Welcome everyone who's out there listening and on the recording to the 2025 OpenVSP workshop. Um, and I'll just go ahead and get started. So I wanted to first talk about some of the things that influence my perspective on creative productivity and some of the technology things that we maybe have something to do with. And there will be a point, I promise. There was some interesting research done back in the late 70s and early 80s by IBM predominantly, looking at interactive response time and what that meant for creativity and productivity. And they did some studies, and this was mostly using dumb terminals interfacing with mainframe computers. And so what they're looking for is the system response time down here on the x-axis is what the time was between typing in an entry to the dumb terminal and when you got a response back from the mainframe. And of course, what they found was that there was this highly nonlinear effect of getting very, very low latency, very short system response time that would result in in a huge increase in productivity and output, how many transactions someone could handle. And there was lots of other research that was done similarly, looking at other measures of systems response time in different cases and looking at what was the productivity coming out. And the short version of this is that in a creative process, your ability to be creative and stay focused on something and to iterate on ideas and to produce output is very much related to how quickly the system responds. And so that can be very short latency, like these, where they're measuring it in seconds or milliseconds, but it can also be much longer. So, for example, if you're doing an analysis and that analysis takes a week to run, then you get very little interaction with it, very little creativity, because every time you spawn off a job, you now go do something else for a week while you wait for a result. And then when that comes back, you have to iterate. And that kills that iteration process. Whereas if you can do an analysis that comes back in seconds or minutes, the shorter time, the better, then it is much, much more conducive to a creative process, an iterative process of design and how we work. So that background really motivates a lot of why OpenVSP is trying to be so fast and do so many of its analyses so quickly. So let's talk about what geometry does in the role of aircraft design. Really, geometry is the start of all kinds of analysis and design. It is the first step in all of these things: aerodynamics, structures, acoustics, mass properties, RCS, all these things. And we think about back when we were in engineering school, right? When you took statics, one of the most basic engineering classes, at least when I learned statics, step one was always draw a free body diagram, right? When you start engineering analysis, you start with the geometry. And it really, that's pretty universal across most analyses. What's interesting though is that and that's true across the whatever the analysis is, whatever the fidelity is, and the shape is that common denominator. However, in practice, there really is not much commonality between these because of the disparate needs of the analysis of these different things, right? Aerodynamics cares about the OML of the aircraft, whereas packaging and layout cares about all the things on the inside of the aircraft. And they couldn't be any more different in terms of their geometry needs. So the true geometry, what does that mean? What is the true shape of the airplane? And as it turns out, if you go out and walk around in an aircraft, right, the actual physical manifestation of it, that true shape really doesn't correspond one to one with any of the particular geometry analysis representations that have gone into that, right? The CAD model is typically built with a single analysis intent. If you're building a CAD model for manufacturing, then you build the model one way. If you're building it to check the integration and maintenance and reachability, can the mechanic get their arm up in that nook and cranny? You build a model a different way. If you're going to do a structural model, then you build the model that way. And often the structural elements don't actually correspond to the CAD model. And what I mean there is you may use beam elements to represent something like a hat section without actually modeling the detailed geometry of that hat section. And of course, aerodynamics, you care about the OML, and then the propulsion is maybe done as a boundary condition. And so, that there isn't necessarily, the analysis doesn't always have to match the geometry in a primitive way. We usually glance over this because we understand what's going on. But in terms of representation, there's actually significant differences here. There's also a modeling gap in the way that we approach geometry and analysis. Historically, every analysis tool had its own geometry engine built in. And so every analysis tool had its own integrated geometry stuff. And it used its own inputs and it performed its own analysis in its own way. And then the sort of what you might consider the more modern approach is using CAD. And so then CAD would then feed a very general purpose measure, whether that was for CFD or FEA or other tools. And so we go from CAD to some sort of an elaborate pre-processing tool to then prepare the input to our code. And, the CAD approach is nice because you might end up with one representation that feeds multiple analyses. But again, you don't really, because you have to model it differently in order to achieve that. Whereas the first approach means that if you have 5 analyses, you end up with 5 different geometry representations, and not just mathematically and conceptually what they represent is different, but the variables, the inputs and the parameters that represent them are usually different. When you put this together in an actual productive engineering workspace, you usually end up with a single flow from a representation through to a single analysis tool. And this is just human nature, right? We don't have the resources to go and invest in many, many analysis tools and many, many workflows. And so when a company invests in, say, automation and validation and experience in training their team, right? When you invest in one tool, which is the full stack from geometry processing all the way through to a result, when you invest in that, that becomes the tool you use for everything. You use that tool for all levels of analysis, whether that is the best choice or not. And so we end up with a de facto very little choice in analysis fidelity. And if we think about different fidelity levels and different analysis disciplines as a matrix, that we would ideally, in my opinion, like to have as a densely populated matrix that we can choose our analysis and our fidelity based on the problem at any time. In reality, we end up with a very, very sparse matrix where we're lucky to have one analysis for each discipline at all, much less multiple levels of fidelity. So these representations of geometry, this is kind of what I'm talking about. We might represent a wing with an airfoil stack up on the left, or a wireframe drawing, or a wireframe representation, or a smooth, analytical Bezier surface representation up on the right. We might have an unstructured surface mesh, or maybe a panel code mesh, or maybe a thin potato chip vortex lattice simulation. Down on the left, we might have a finite element mesh representing, the wings and the ribs and spars and the wing surface. We might have an equivalent flat plate representation, or down on the bottom right, we might have an equivalent beam for that wing. And so right here's this, very quickly 9 different representations of a geometry that would feed different analysis tools. And, in a traditional CAD workflow or in a traditional geometry workflow, these aren't easily available. And when I made this figure first, many, many years ago, I had to cartoon all of these up. I had to sort of manually create them. And it was a bit of, movie magic to make this figure exist. Whereas today, OpenVSP basically supports all of these directly, which is, I think, really exciting. So really, in a VSP setting, all of these representations can be generated from VSP. And so the shape, the fundamental, what is the geometry as far as what OpenVSP stores and keeps in memory and saves to disk, right? We're not saving any of these representations. What we save is the parameters, right? The parameters that you're adjusting in VSP, those parameters are the geometry. And all of these different representations are created as needed. Sometimes that's on the fly, but sometimes it's through an explicit action. Now, the representation, it relates to the discipline, and as I've said, and it also relates to the fidelity. So, a vortex lattice simulation needs one representation, a panel code another, and CFD another representation. So the representation may relate to fidelity, but the important thing here is that people often mistake that for the stage of design. Some people think that you use low fidelity tools in conceptual design and higher fidelity tools in preliminary and then highest fidelity in detail. And that's not actually how the mapping goes. There are times when it is appropriate to use low fidelity tools very late in the life cycle of a project, and times when it's appropriate to use high fidelity tools very early in the life cycle of a project, right? So it's not this monotonic low to high as a program progresses. So let's talk a bit more about fidelity in the design process. This is my soapbox. I get this moment. So first I'll share a figure from my late friend Lee Nicolai's textbook. This is from the 2010 edition of his book, but if you look in the 1976 edition, it's the exact same figure, it just wasn't in color. And so Lee's talking about the conceptual design process and the aircraft design process from conceptual to preliminary to detail. And when you look at this, we're looking at, well, what are the things that are being considered? The overall shape, sort of the details here, and then, really the details, the ply layups and the structural details. We look at the results and what's the output. And the point here is all of this is about what decisions are being made in the design process, not about how those decisions are being made. Nothing here talks about how they're made. And so sometimes that to make those decisions, we need sophisticated analyses early on, but sometimes we don't. And so, in this process, there are times when you need a sophisticated transonic CFD code in early conceptual design. And there are times when you're going to do paper and pencil analysis of the loads on a bracket in a structure very late in detail design. And that's entirely appropriate, choosing the fidelity as you go. I have a little bit different perspective up here on conceptual design. And what I really like to teach, and when I did that, is that the real outcome of a conceptual design process, of a conceptual design program, the real outcome is not the airplane design. The output of that is actually a go, no-go decision by your leadership. And a conceptual design process is all about leading up to that go, no-go decision. Does this program continue? And there have certainly been cases where successful conceptual design processes have gotten to that point, they've made a go decision, and then they throw out the design and they start over. And that's okay. And so when you think about conceptual design decisions, and when you think about the conceptual design process, you need to think about them with respect to that go, no-go decision. Does whatever rabbit hole you're going down and whatever, fidelity and whatever decision you're trying to make or add to the simulation, does that thing influence whether it's going to be a go or a no-go decision? And if it doesn't make a difference, then you're not spending your time on the right thing. You need to be focused on what influences the go, no-go decision during conceptual design. So OpenVSP uses parametric design, and I talked about how the shape and what the representation that VSP has really is those parameters. And what I'd say is that's true throughout all phases of design. It's just what those parameters are evolves. So early in the conceptual design process, we have these very high level parameters like aspect ratio, area, sweep angle, taper, thickness to chord. And then as we move to preliminary, we're talking about more nuanced, twist distributions, thickness to chord distributions, a complex wing plan form, detailed high lift geometry, control surfaces, all of this kind of a thing. And so we have more parameters and they've evolved. And then we go all the way to detailed design, where to some extent the generalization of parameterization may break down, but the parameters at that point are the angles and the dimension drawings and what are the dimensions in that drawing. And so again, as we move through design, what phase of design is based on what decisions are being made, not how they're being made. So let's talk a little bit more about the design process. Another soapbox for me. A rational aircraft design process. This is the way it should work. We start with a mission, and the mission is there to answer the question, what is the aircraft going to do? And we move from there to the ConOps, and how is the aircraft going to do that? So what is the aircraft going to do? We're going to move people around inside a city. The ConOps, how are we going to do that? We're going to take off and land vertically, and we're going to move very quickly, and we're going to recharge very quickly. And you take your mission and your ConOps, and then you can start to set the requirements. You use those and you figure out, okay, I need to carry this many people. I need to go this fast. I need to fly this often. I need to be able to take off and land out of this size of a heliport or a landing field. And we're quantifying the requirements for that ConOps and for that mission. Only at that point should we then move to starting to define the concepts. And here, when we're looking at these concepts, we're looking at the system architecture. Is this going to be a jet wing? Is it going to be a tilt wing? Is it going to be a fixed wing aircraft? Is it going to be distributed electric? Is it going to be, just whatever that conceptual architecture is? You can think of these as discrete big block things. And then when we have a concept, then we can move to these more design decisions. And where the concept decisions are laying out the system architecture, the design decisions are actually then tuning those continuous parameters. Oh, well, what's the diameter of the prop? What's the wingspan? What is the thickness? So we go through a discrete variable phase, and then we move into a continuous variable phase. And this is the way advanced design should work. And note down here at the bottom, these last two steps, 4 and 5, is really where we would like to look at many concepts. You're not really doing conceptual design if you don't compare at least two concepts and decide which one is better. So if we want to look at many concepts and concepts, we are going to be doing iteration, and we are going to be doing trade studies. We're going to be doing trade studies to set the continuous variables, and we're going to be doing iteration over concepts. And so we really need to enable as much speed and as much iteration in those two steps. Now, as we look at the larger picture of a life cycle, we move out of that conceptual design, we go to preliminary, detailed design, test insert, manufacturing, tooling, operations throughout the whole life cycle of the aircraft and disposal. You'll notice as we move through this process, we have less and less design freedom, right? We've committed more and more cost. Even if we haven't spent that money, when we decide that we're going to do a particular engine architecture, or when we decide we're going to use all composites, or when we decide, how we're going to lay up those composites, we are committing costs. We haven't necessarily spent the money yet, but we've decided that if the program continues, we're going to have to spend that money. And as we commit those costs and as we decrease our design freedom, the cost to change a design increases exponentially. And that's obvious that if you need to, make a major change to a design after you've started manufacturing, that's incredibly expensive. But it's true through all of these steps that the further you go in this process, it's more expensive to make a change. And that means that you just want to make all those changes up front. You want to make those decisions when it's cheap, before you've committed the cost, before making that decision gets expensive. And so you want to do this in a rational way and proceed. Now, unfortunately, the reason I talk about the way it should work is because, unfortunately, very often these days it seems that it doesn't work that way. And I will say that there's a lot of quote unquote innovators out there in the aircraft design space where the process doesn't follow what I've laid out, and instead it typically starts with somebody who's had a decision about what the concept ought to be. And they make that concept decision up front. They've decided this is the concept. It's probably an arbitrary decision because they didn't actually do any trades or any comparison, and they make that way too early. And now that they have their concept, they hire an engineering team and they throw that over the wall and they say, make it work. Try and figure out how to make this happen. Take this concept, make an airplane. And what we find is as they proceed in that, then they go out looking for a mission. Okay, well, we've got a concept. We're going to have an airplane. What on earth is this thing going to do? So we go searching for a purpose. What's the point of having this aircraft? And they move from that to then, well, now we've got an aircraft already defined, and now we found a mission. So now we force the ConOps to fit our aircraft. We're just trying to shoehorn it into a particular ConOps. And this process is very awkward. And the thing that's missing from this is the requirements, right? Nobody ever states the requirements. And so the engineers in step 2 are fundamentally working to an ill-posed problem because they don't have requirements to design to. And they're just going to treat the requirements as a fallout. It can do whatever it can do. And whether that meets the mission in the ConOps or not, oh well. And what's really missing here is iteration. And you end up with teams that are completely married to a concept. And that's, fundamentally a bad way to go. And I've seen way too much of this. Now, I'll juxtapose this and I'll put in with this that, I think fidelity is used poorly today in engineering. I think it's all too easy to push for quote unquote higher fidelity. There's this constant push. People seldom get fired for using too high fidelity of analysis. And Moore's law justifies and enables this continuous increase in fidelity. And there I'll just say that I'm saying the number of floating point operations per answer. What is the computational cost? Even though that's often increasing fidelity per answer, but at constant calendar time. I feel that if you went back to the early days of CFD and you tracked the wall time of the top of the line, state of the art CFD analysis, that it would stay about the same. It's about 1 week. And from the birth of CFD to today, that's remained essentially constant. The top of the line CFD analysis remains 1 week. And I would argue that that is not because that is the analysis fidelity that is required or that is needed, but it's just because that's what they can accomplish and what they have the patience for. So the pursuit of fidelity is actually separate from the actual needs of programs and analyses. So I'll go a little further. We often see, and I'm talking specifically in eVTOL, just because that's an area that I have a lot of familiarity with. You'll see these marquee CFD calculations where you have an animated high color rotating blades, elaborate color video that's the result of a weeks-long supercomputer analysis. And what I'd say is that these analyses are essentially meaningless in the design process. And the reason for that is that they're almost always done at a single operating condition and at a single, angle of attack, forward speed, climb speed. These are over-controlled vehicles with many different flippers and RPM and rotor pitch on them, so many, many degrees of freedom to control them. And yet the simulation is done completely untrimmed. It's just a fixed RPM, fixed angles on everything that we can do it. Whereas in reality of this kind of vehicle, it's the off-nominal analyses that dominate the design, and you need tons and tons of these. And so these one-off stunt calculations are actually meaningless and perhaps dangerous. The highest fidelity analysis tools become unavoidably black box, right? Even if you are the developer of a Lattice-Boltzmann CFD tool, you lose intuition for what changes to the inputs are going to have in those detailed outputs. even the most expert person on these ends up being forced to use these tools as a black box because we have this opaque mapping of inputs to outputs. They produce gigabytes of output on every case, and then we boil it down to just a few coefficients. And really the outcome for this, in my opinion, is that when an engineer chooses to use a high fidelity tool, they may or may not have understanding of the problem. And that choice of using that high fidelity tool does not demonstrate that they know that they understand the problem. They very well may just be, I don't know, so I'm going to throw the high fidelity at it. On the opposite side, if we go back to this rational design process where we need to look at multiple concepts and we need to iterate and do trades in order to make those decisions when they cost the least, fast, inexpensive tools are essential to conceptual design. We need to look at more concepts, more iteration, more trades, more insight. And all of this enables the creative process, getting that response time down and being able to do these things. And so the goal should always be, in my opinion, to use the lowest fidelity tool possible for all decisions. And I'm not saying that recklessly. You have to know that the tool is sufficient to make the decision. You have to understand the problem well enough in order to know that that tool can support the decision you want to make. And so consequently, if you do this and you're successful, then appropriate use of low fidelity tools does demonstrate that you understand the problem and that you understand the decisions you're making. So let's talk a little bit about OpenVSP. That's my rant to start the morning. Here we are, we're in 2025. I think we've had 13 or 14 different OpenVSP workshops, which has been amazing because when we did the first one, we didn't know it was going to become an annual event. It was just the OpenVSP workshop. So, I ask out there every year, I ask how many of these have someone been to? And ask yourself also, what version of the software are you using? And so right now, the current version is 3.43.1. And if you're using 3.25 or something, come on, guys, it's time to update. Since last year, there's been just a litany of features that have been added. I'm not going to read this list. There have also been countless bug fixes. A lot of the workshop this year is about talking about these new features. I'm really excited about a bunch of them, and I hope that you guys are going to enjoy it. It should be a lot of fun. Here's the agenda. This is posted on the wiki page that if you found the link to come to the stream, you know where that is. We're going to take the calendar here is a little bit odd. I have Pacific time on the left, on the west, and Eastern time on the right. It's very US centric, but hopefully that gets most people oriented for what's going on here. And so we have a break for lunchtime on the East Coast and a break for lunchtime on the West Coast as well. And after my talk right here this morning, we're going to turn it over, and Brandon is going to do a great demo of modeling a realistic and interesting aircraft. And that's my last slide. I'll go look at the comments to see if there's any questions that I've missed. And I'm really just thrilled that people have joined us and that we get to do this today.